going to take you through two separate response fitting methods today, which are both discussed in the textbook. This one, the idea of just fitting step responses using a general curve fitting tool, is kind of mentioned in a throwaway paragraph in the textbook. It's not really picked apart very well. I think at some point they have an example where they say that they've done it and they just report the results. They don't actually go through the motions of how that would happen. This notebook answers that question. But I want you to understand a very important thing. Old school, this is very old school. This idea of having a step response is old school. It's very reliable. But right now, and when I say right now, I'm not saying like right now in the time that the textbook was written. Like right now, if you go onto a plant, very few people are doing pure step tests. What I mean by a pure step test is this idea that we've kind of covered to death already. The idea that I'm going to have some kind of a system. Now remember, you know, it depends on how you want to think about it, but you've got a system with an input and an output. And in the Laplace domain, we think about that being a transfer function in a block. But obviously on the real plant, there's an actual tank or an actual heater or an actual big piece of equipment that you are changing values for. And every time that we do this, every time that I tell this story, which by now should be very, very familiar to you, you have to understand what that implies in the real world. So for instance, what this would imply is if you were driving your car, right? So there's the steering wheel of your car, dashboard. Okay, so you're driving along. I really have to get better at sketching. Okay, so you're driving along. And your friend proposes a step test. What does this involve? If we're trying to figure out a model that relates the steering wheel to the direction the car is driving, a step test would involve making a very immediate, very sharp rotation of the steering wheel in some direction. Okay, so we start at steady state, which is the steering wheel straight ahead. And a step test would be yank the steering wheel a certain angle to the left and keep it there until we see what happens. So how keen would you be to do such a test? Let's say I have a tank here, right? I'm doing this step testing. I'm opening up that flow. But let's for argument's sake imagine that these units here are meters, right? And let's say that this is let's say the gain is something like 5. Okay? But let's now also imagine that the actual dimensions of this tank is 2. Would you be keen to complete such a step test? In other words, an ideal step test where I increase the flow rate by some fixed amount, I let it reach the new steady state. And assuming that the new steady state is 5 meters, I wouldn't be keen to do that on my plant. In fact, even if I were keen, even if it was like, you know what, the boss is away, you know, let's just go for it. I couldn't do it. I couldn't actually do it. Because in reality, my level measurement would just level off at 2 meters. Right? And my feet would get wet. But I wouldn't be able to measure in real terms an actual ideal step response. So what's the solution? A lot of you are thinking, wait a minute, I have a very special solution here. I don't have to do a unit step, right? I can just do a small step. But then it becomes complicated. Let's say, again with our level here, let's say that's level over time. And let's say the level is hovering around 1 meter. And when I say we're hovering, I'm saying, like, as all real measurements do, there's some noise in the measurement signal. There's maybe mechanical noise in the tank itself. Maybe it's being mixed, so the level itself is actually not just like crystal clear, perfect. It's kind of moving around. There's electronic noise. There's all that kind of stuff. And now you propose, okay, cool. I'm going to make a change that will have the effect of, so let's say that's 2 meters. I want to make a change that has the effect of changing the moving to a new steady state of 1.5 meters, which is about there. Right? And so what that would look like with all this hairiness is something like this. And so you'd have a problem. You'd have a problem of distinguishing between the noise and the input, the actual effect of the input that you've made. And so these two effects, the fact that a true step in many cases on a plant would be dangerous if I made a step large enough. Also, as a side note, it takes a very long time. It may take a very long time for the system to reach a new steady state. As an order of magnitude kind of feeling thing, I know a lot of people complain about the TC lab being slow. If you're working at a place like Sasol, those big distillation columns, they typically have a time to steady state in the order of about 12 hours. So what that means is if you make some kind of change like this, you make the change and you do other stuff. Right? You don't sit there watching the screen, you do other things while this is happening. Of course, there are people who are paid to watch the screens and make sure that nothing blows up, and those people are very cross at you now because they are paid to keep the plant running at some optimal position, and you have just told them, I'm going to push it away from that optimal position and keep it there for a while. We're going to be making off-spec product for all of that time. And why? Well, you know, I just want to get a feeling for how it works. Not popular. Okay, so these, and so this is what I mean by old school step testing. And if you are in the position to do this, and I want you to kind of understand how the technology has actually made people's lives on the plant better, because the old school fitting methods would be something like this. Now, what I've done here, you can go through this notebook on your own time, but I've generated some data. I haven't measured it. So I've just generated a relatively high, that's a 4th order polynomial at the bottom there, so that's like 2 over 4. So it's a net second order, or net third order system. But the step behavior looks like this, and you can see that it's definitely a little bit more complicated than a straight second order. It's got this little weird little bump behavior happening there, which you wouldn't expect from a straight second order. But what I've done is I've taken that step response, I've added some normally distributed noise, which is kind of how measurement noise usually distributes, and so this is now kind of a synthetic data set. This emulates the idea that we're working on a plant and we've read these noisy data. And again, you could use the very old school techniques, Smith method and all the table-based methods, but now that you are armed with yesterday's lecture and you know that this tool called CurveFit exists, you also know that you could simply take the step response and use CurveFit to estimate the parameters of that system. Now, I've taken the time to code both the first order plus dead time and the second order plus dead time step response functions, the analytic response functions, into TB control. And so you can now just kind of import them from TB control responses. Those functions are parameterized. They have, again, a time constant and a lag. So you can basically specify these parameters. For the second order process, you have a tau and a zeta, obviously. And what I really recommend when you are doing fitting problems of this kind, one of the ways that you kind of ameliorate or counteract this problem that it can be hard to guess the initial values. One of the ways that you can kind of fix that problem is by getting a feeling for what your response function actually looks like with certain parameter values. And I find interact really good for that. I think most of you have maybe come across this function before. It just allows you to kind of take a function and add these sliders onto it so that you can plot the results in this way. Let me just hide a little bit of this. Is there a way of hiding that? No, okay. Yeah, that's big enough. Okay, cool. So we can see that the gain has the kind of expected response. So we know, okay, the gain should be kind of around 2. That time constant looks about right to me. If you look at it looks like that is the same as that, but just shifted up. And so I'm just going to shift it back a bit. So the time delay is probably a bit less. And this y0 is just the initial value. So obviously you want to add back that initial value. So that doesn't look half bad. And so you can kind of see what these functions look like. I recommend that you also take this notebook and change it so that you parameterize the second order plus dead time, so you can also get a feeling for what that looks like. But in the end, the invocation of curve fit is very understandable. Hopefully, if you followed yesterday's lecture, we pass a function. This function takes the times as its arguments, and the curve fit is trying to get that result with first order plus dead time at these times with these parameters to be equal to these measured data. And it works pretty well. Now again, it works well in proportion to how close you already have the parameters. And so I always recommend this kind of 1-2 process, right? Like start with your eyes, get a good feel for it. Remember, you don't have to do the interact. You can also just estimate, right? So you can say, look, looking at this, if that was a unit step, clearly the gain is about 2, right? Because it's 10 minus 2, 12 minus 10. And looking at the kind of general time scale of this response, if it's a first order response, maybe the time constant is about 4. If it's a second order response, maybe the time constant is about 2, right? You can estimate eyeball that easily knowing these other rules, but just like from a very loose version of this. I would definitely, like if you're thinking about tests and exams, there's no way that a normal human can look at a graph like this, like with their eyes and their brain, and come to like 2 digits of precision on any of the parameters. So it's very approximate. You know, you're going to kind of eyeball it and you're going to estimate a guess. And I like this idea of starting there and then using these optimization routines to get like a polished value, like a slightly more closer to the answer value. And so that's basically what we see is we can do the same thing with the second order. And if we plot those results, we can see both of them do a pretty good job at this approximation. And now while I'm saying this within the context of parameter identification. So, or parameter estimation is another word that people use for this. This is this idea that I have some kind of shape that I've assumed for the model, but I don't exactly know the parameters. And you may find yourself thinking that sounds very similar to the kind of problem that you have in project part 3. Right? So you've made some decisions about the shape of your model, and you've made some initial starting guess at the values of the parameters, but now you would like to change those parameters to more closely resemble the things that you've actually measured in reality. So this strategy is basically the same kind of strategy that you can use there, and that would be necessarily nonlinear. So an important thing to understand here is that in most cases when we have a generalized response function like this, the parameters are deep inside of that function in ways that are not easy to linearize. It is kind of possible for the first order response, there is a little bit of manipulation that you can do if the dead time is not very long. You can draw logs and then get back to linear regression, but that's kind of an edge condition. It's not very reliable in my experience. But partly because of all these other things that I've just been talking about, the noise and the problems with doing pure step tests are not used very frequently in the industry any longer. Instead, people will use a completely different strategy, which is based on linear regression. And I'm going to kind of just walk you through the logic of that in today's lecture. So this is an important technique. It's important for you right now, just because it is something that you can do to kind of optimize the parameters of your of your model for the project. It's also important, I think, to kind of get an understanding of how things work, and for systems that are safe to step. And then if you think about what kinds of systems that would be, these are systems that don't exhibit all the things that I was talking about. In other words, if the system is relatively, or has a relatively low noise band, right? So if this is not true, if instead I can make a small change and kind of measure a nice step response on there, and I can clearly distinguish it, and I'm far away from any kind of safety bounds on that system, a step test may be a perfectly reasonable thing to do. Of course, you'd still be annoying people because they probably were operating here for a reason. And that reason usually is money. Again, thinking about places like Sasol, when Sasol Secunda is shut down, they are losing money at a rate of about R1 million an hour, as a kind of a general rule. And so what that means is if they can avoid an hour shutdown, that's like R1 million that they've not had to spend. And so if you think about it like that, translates to quite a lot of engineering time. You know, you can pay a lot of people to make that stop if you're hemorrhaging money at that rate. So people won't be keen to definitely shut down the plant or kind of stop operations, and definitely if they're making things like off-spec product, or if it's affecting the quality of the final product, that is almost guaranteed that they won't allow you to do this. And so what do we do instead? So maybe just let's draw that line sharply. Step tests are useful. If you can do them, you should, because they are simple, they are easy to interpret, and the math is easy. Okay, you can do them easily. Everybody understands basic step tests. What happens today is we do a whole different kind of test. It is alluded to in the book, but this kind of test is in many cases called a pseudo-random binary sequence. An important property of this is, I want you to see a very important property of these kinds of sequences. These kinds of pulses or random pulse tests are a lot more acceptable in terms of the disturbance on the plant. So for instance, back to the car analogy, that would be like driving a new car and just like twitching the wheel a little bit and like bringing it back, just to kind of get a feel for how responsive the car is. Which is a whole different proposition, right? From, oh, I'm going to move it and keep it there and like drive into a ditch, which nobody does, to, well, I'm going to jiggle the wheel a bit, right? Look back and forth and get a feeling for what it does, which is what everybody does, right? Like everything that you interact with in life, the first time you do it, what do? You kind of move things around just a little bit, like conservatively at first, just to get a feeling like what will happen if I do maybe a little bit of this. Oh, okay, not much has happened, I'll maybe make it a little bit bigger. Okay, cool, I can see the effect now. That's much more like we normally interact, because we know it's relatively safe to make changes of this kind, which have kind of this stationary mean. So it's moving a little bit up and down, and I'm making small changes, but I'm keeping them there for a while, and I'm sometimes doing it for a short time, and sometimes doing it for a long time, and I'm getting responses that then kind of meander. So if that's you, and this is why, I then get kind of responses that kind of meander around like this. And importantly, at this point, if I'm doing this kind of thing, it is usually no longer possible to eyeball it. Because if I'm making these changes in a relatively short time frame, and I'm making them and kind of jiggling things around and seeing how things happen, some of the early effects actually wash through to the end. You know, so some of the stuff that I'm seeing happen over here, you know, this change is the sum of all of these different changes to get there, which is very, very hard for a human brain to kind of untangle. And Obviously, what's happened to make this a reasonable strategy is that we have been using computers to do that fitting for us. One way of doing this is just the straightforward curve fit way that I've just explained, right? So you could just say, well, I have this thing as my input. I can use maybe something like ALSIM, take my control transfer function, push that signal through it, and then repeatedly change the parameters until I get a good match. It turns out that that process is quite computationally intensive. So it's fine if you just kind of do it once or twice, but if you're doing it for a very long time, it takes kind of linear time to do that simulation, right? So, and you guys have seen this, like on your simulation of your TC lab, it starts taking a long time. Like just running that for loop takes a long time. And so if you're running that for loop and then changing the parameters and running the for loop and changing the parameters, it can take a really long time to actually get to the actual parameters that you want. And so there's a further enabling technology that kind of enables us to do these fits really, really quickly and also really, really reliably. Can you guess what is at the heart of this method? Can it be linear systems and the kind of stuff that I was talking about yesterday with linear regression? Yes, the answer is, of course. We need to think about models in a slightly different way to make that happen, though. This is the first time that you've encountered models of this kind, but I want you to understand that this idea of what is called a discrete time model is a relatively simple permutation of the kinds of models that we've been writing down so far. Remember that we've been writing models of the kind, I'm just going to write down the y part here. So if I have something like dy dt, and that's going to be like a y plus b u. This is a differential equation, okay? So it's a differential equation because it features these vanishingly small dt elements. And I'm just going to like highlight the fact that these things are all at the current time. The way that we can kind of approximate this differential equation in a form that allows us to write down linear equations that feature these same parameters is to do the thing that you probably kind of have in your mind about approximating derivatives anyway, which is to use something like a first order finite difference approximation. So remember this is dy dt. Right? dy dt is that slope. If I sample at certain times, let me just, so that's now time t, right? Let's say that I'm sampling at some sampling interval delta t. I can say that I can approximate that slope by this change in y over the change in x, or in this case, t. And now I have a difference equation. The difference here is the fact that delta y will be y at t minus y at t minus delta t. Right? And the delta t will simply be that delta t. So that will be a constant. Okay? Now, do you see what's happened? I've changed the differential y into a difference. And this is why we call these things, these new equations, difference equations. Because we're going to say, if I were to do this, I now have this thing, y of t minus y of t minus delta t is equal to a of y of t plus b of u of t. Right? And so notice that I'm just effectively indexing, and I'm changing from a differential equation whose solution is a function y to a difference equation whose solution is simply the values of y at the sampling points. And for people in the digital generation, this difference appears not to really make a lot of difference because you think about curves and things being like something that you would find in a spreadsheet, but it's fundamentally a different idea. You couldn't show the solution of a differential equation correctly in a spreadsheet. Does everybody understand that? Because the solution to a differential equation isn't values, it's a function. But the solution to a difference equation is the values. And there is no function. Importantly, there is no version of solving a difference equation that results in a function as an argument, as an output. The only thing you get out is the values at those points in time. And so there's a little bit of magic going on in this book, which I would like you not to think too much about during this lecture, because I just want to kind of walk you through the basics. I strongly recommend that you kind of watch a couple of YouTube videos about pandas, because pandas is amazing. I'm kind of using pandas here to make some of the indexing tricks that I'm doing a little bit more easy. But you can see that here we have a difference equation. And when I say difference equation, you can see that here's yk. And at some point, this yk minus 1, where k now is the time index, right? Maybe used to be on the left-hand side, and that used to be like yk minus 1, and some function on the right-hand side. I've just written it in this form, which is the forward form. It's like, how do I calculate the next y from all the previous y's and all the previous u's? Is everybody clear on the link between what I showed you just now and this equation that's here? We're going to dig into discrete models in a great deal of detail later, the analysis, and like also we've got a special notation that makes all of this easier. The piece that I want you to understand today is just that writing equations in this difference equation form allows us to identify these parameters using linear algebra techniques. And it's kind of the modern standard for process identification. Notice here that we make no particular assumptions about the shape of U. In other words, we're not saying it has to be a step, it doesn't have to be a pseudo-random binary sequence, we just have to know what the values were at particular moments in time, that's all. So we just need a spreadsheet that has the values, that's it. Now I'm gonna like load a spreadsheet like that into pandas over here, and basically what we have is we've got yk and we've got uk in a table. Some people in England say maybe we should remove this column. I don't know. The way these data look is that we've actually done effectively a step test. So notice here what a step test looks like when we're using relatively large time steps. If you're thinking, wait, that doesn't look like a step, remember we cannot get a crisp, perfect 100% vertical change when we're using finite step sizes. Right? All we can do is we can have it be 0 at one time step and then the other value at the new time step, that's it. That's as good as we can get. Now we're going to do the same trick that we did yesterday. We're going to write down this equation once for every row of the data that we have. In other words, once for every value of k. And when we do that, I've kind of written a program that writes out the equation so that you can see the form, right? Notice again that we have a whole list of equations, and the y's and the u's are known because they come from the data. But the b's and the a's are unknown. And if you look at that carefully, you see it's exactly the same shape. This idea is the same shape as we were analyzing yesterday. We have these known values and we have these unknown values. We can factor that into a form y is equal to x times beta. Beta in this case contains a1, a2, b1, and b2. And the coefficient matrix is all of these things. Now, there's a pattern to these things. You can see because of the way that we're doing it, we're going time. Every time we're just shifting up the data 1. And you can see we've got 0, 0.058, 0.22, and so on. And then we've got the same pattern, but like shifted down 1. And this is a general rule. So if we have y of k minus 1, minus 2, minus 3, and minus 4, every time we write that equation down, we'll see this diagonal pattern happening. So you can see it more clearly in the spreadsheet where that 0.58 is the same as that 0.58, it's the same as that 0.58. And matrices that have this behavior are called Toeplitz matrices. So Toeplitz matrices are matrices with constant diagonals, or that have all the same numbers on the diagonals. And so we can use the Toeplitz function to construct the x that we're looking for. So we just supply the values there and the values at the top, and then it fills in because that's obviously just the diagonals. So once you know, for a Toeplitz matrix, once you know the top values and the side values, you know all the other values because you just fill in the diagonals. And from there, it is now no trouble at all to do exactly the same thing that we did yesterday. We do a least squares solve using that y and that coefficient matrix, and that gives us the parameters. Now, understand that this is amazing, okay? No guessing, no weird side things of like, first we need to investigate the data. The only proviso is that we've sampled in a good way. What I mean by that is, obviously if you're doing a step test of 5 hours and you've only sampled like 2 seconds of values, but you've sampled like 1,000 of them because you sampled at like 0.01 a second, you're not actually going to capture the dynamics of the system, and the fit will fail in the sense that you won't actually get the values that you're expecting because you don't have enough data to cover the full spectrum of the behavior that you're seeing. So you need to choose your sampling points wide enough spaced so that it actually captures the dynamics, right? But within those constraints, this method is really great, and it is the workhorse, this least squares estimation. And this is what modern engineers typically mean when they talk about step testing. When they say, oh, I'm going to step test the plant, they don't mean I'm going to make actual steps. They mean I'm going to hook it up to a tool like this, and the best ones can do this fitting incrementally. So it can start and do a couple of fits and start fitting and estimate the certainty in those parameters, and then stop once it's sure enough, which means that you spend less time fitting, you do less disruption, and you get better results.